Hello, everyone. My name is Zhouzhou. Currently, I'm an assistant professor of Southeast Missouri State University. Today, I present our new paper, Construct Forensic Evidence Networks from Information Fragments. All the authors are associated with the CS Department of Southeast Missouri State University. Here's the outline of today's presentation. It includes 4 parts: the introduction, literature review, and proposal and the experiment. And the last one is the conclusion and the future work. In the introduction, we will discuss the jigsaw puzzle problem and the meaning to digital forensics. This picture shows an example of the jigsaw puzzle problem. So as a summary, such a problem is about stitching the parts together into a full picture. And it belongs such a problem category that is infer the global information from local data. And the solution for such a problem will be, for example, get clues from each part based on the edge shapes and the colors. So both shapes and the colors can be used to conclude the global information. Here, this picture shows a simplified jigsaw puzzle problem. Why it's called simplified? Because all pieces are equal size. Okay. And its solution relies on the clue from each part, but only based on the edge colors. No shape information could be used to figure out the solution. Okay. So a solution for this simplified problem is actually not simple because of lacking the shape clues. Why we need to study the jigsaw puzzle problem and apply it in the digital forensics? In this paper, next 10 years, the data C issue in digital forensic investigation, they also list a lot of issues. Okay, among them, there are 5 issues. Okay. The first one is the growing size of storage. The second one is the increasing prevalence of embedded flash storage and the proliferation of hardware interfaces. And the third one is the proliferation of operating systems and the file formats. The fourth one is analysis of multiple devices followed by the correlation of the found evidence. The last one is use of the cloud. Here, this picture actually is modified from this paper or this article. As we can see, the forensic investigator is trying to correlate 2 information pieces from the data C. Okay, but as we can see, this guy only has limited equipment or tools to facilitate his work. So the summary actually, this picture implies the data size growing but scattering trend and the time pressure in digital forensic investigations require good models to help correlate information fragments. The jigsaw puzzle problems are like the above information fragment correlating problem. So a good solution for jigsaw puzzle problem may inspire the digital forensic work related to correlating fragmentary information. In the literature review, we actually studied the mature models to correlate information pieces. Okay. One is the file carving model. The other is the panoramic model. Both are well-studied fragment model. Okay. Regarding the file carving model, a file fragment only has one prior and one successor. But an information fragment may have multiple connections to others. So file carving theories and models cannot sufficiently describe the high dimension evidence network. And the panoramic model utilizes the temporary and the spatial overlaps to build adjacent relations between fragments. That means there should be some overlaps to be used. However, when we try to correlate information fragments in digital forensics, those information pieces may not have overlap. So both models cannot fit in the digital forensics when we try to correlate two information fragments. That's the reason we would like to use the jigsaw puzzle model in digital forensics. Like in this picture, this is simplified jigsaw puzzle problem. Okay. When we try to correlate two pieces, we can use some method to calculate the correlation coefficient of the edges, okay, to decide if the edges are similar. If the edges are similar, then we can estimate or we can guess they're adjacent, okay, they're probably adjacent. So by doing this, as we know, for example, Pearson correlation coefficients, if the value is absolute values are close to 1, that means a very high similarity. Okay, so by using this method, we can conclude such edges. Okay, may be adjacent at the original picture. Okay. However, we need to handle false negative and false positive cases. For example, this actually represents the false negative cases. These two pieces are adjacent in the original picture. However, if we calculate the correlation coefficients of the two edges, the result is just 0.513. It's not very high. So we cannot conclude they're adjacent by only relying on this correlation coefficient. Also, there's a false positive cases, like in this example. When we calculate the correlation coefficients of the ages of the two pieces, the value is very high. It's 0.918. But as we can tell by our eyes, these two pieces are not adjacent, actually. So we may need to rely on other edges to decide if these two pieces are adjacent in the original picture. So as a summary, we cannot just rely on one dimension, calculate the correlation coefficients to decide whether the two pieces are adjacent. We need to measure multiple dimensions, okay, and get an overall estimation about the adjacent relationships between the two information fragments. So that's our idea. It's quite simple. Okay. And then we try to apply the jigsaw puzzle model in digital forensics in three cases. Okay. This is the first case. It's related to the BTK, the famous BTK case. A killer killed many people. And for many years, his identity was not identified. So many years later, the killer sent a floppy disk to the police office to mark the tracing capability. And the digital forensic investigated the floppy disk and found an RTF file which contains metadata and shows the author is a Dennis and his organization. So from the killer through the floppy disk, through the RTF file, through the metadata, then we can construct a path to this Dennis. And each segment among the paths, okay, we can use one value to represent the correlations between two nodes. Okay, like this one, because the killer sent the floppy disk, so the correlation between the killer and the floppy disk is 1. That's a very high value. Okay, and the floppy disk contains RTF file. Okay. This RTF file is related to the case. It's not a system file like the DOS file provided by Microsoft. We should not blame Microsoft. Okay, so this RTF file is closely related to the case. Okay, and it's in the floppy disk. So the correlation between the RTF file and the floppy disk is 1. And the metadata also has a strong correlation with the Dennis. However, why this metadata is attached with this RTF file? There could be 3 possibilities. So we just guess the possibilities on it. This is the raw data, 0.3, 0.3, 0.4. Together they're 1. Okay. This is rough data. We don't have to get the accurate estimate at this moment, but at least we construct a path from the killer to the Dennis. Then we can try to get other evidence, okay, for other dimension, get more evidence about this case. So later the police try to get Dennis' DNA through his daughter. And the killer also left some DNA in the nail of one victim. Okay. And compare the two examples of the DNAs, they figure out the strong correlations. Then this part we construct from this dimension, we construct a strong correlation between Dennis and the killer. This is another example about associate accounts. So in 3 servers, the 3 accounts, okay, and these accounts own some files, like these 2 files on 2 machines are the same file. Okay, so the correlation is 1.0. However, this account has similar, almost the same picture, but it's in different format. It's in the JPG format. So but the content is the same as this BMP file. So we can assign a 0.91 correlation between these 2 nodes. And again, this MP3 file save the same music as this WAV file, okay? Because they don't have the same format. We cannot assign value 1 as the correlation between the 2 nodes, but we can assign a very high correlation value, such as 0.95 between the 2 nodes. Okay, so, but from globally, these 2 accounts has a strong correlation connection, but these 2 accounts have 3 strong correlation connections. So from multiple dimensional perspective, we would say these 2 accounts are associated. This is another example about applying the jigsaw puzzle model in digital forensics. So these 2 parts of the system, they have almost no similarity. I mean, because the separator is just between them, okay? They're separate parts, different parts. But only look at the correlation, direct correlation, we cannot tell that there has any similarity. However, both of the parts are associated with the system and has a stronger correlation with the system. Okay, then we can construct another path from part 1 through the system to part 2. And if we calculate the metric for this path, we can use the product of each segment value. Then this path has a higher correlation value than the direct correlation. So this can explain the false negative case of the simplified jigsaw puzzle problem. So sometimes we cannot directly infer the hidden correlations between 2 information pieces. Okay. But from multiple dimensional, they may have stronger correlations. Okay. So our conclusion is, through the case study, we show that the jigsaw puzzle model works well in digital forensics. When we try to correlate 2 information fragments, our future work introduce the noisy pieces or fragments to the jigsaw puzzle model, which reflects more realistic forensic environment. And these are the references. Thank you.